Thank you very much, Koei. So we have 5 minutes for questions. So please, anyone have a question, raise the hand, please. In the meanwhile, perhaps I can also ask a question. So I was wondering in what examples have you used these super operators on this force current decomposition? So
Okay. So examples, we can apply the formalism to essentially any cases. But for example, if the jump operators are just the classical one that governs just a single jump between two energy states, then these components will provide some gamma k times the density, the diagonal element, minus gamma minus k times some diagonal element times 2 over Lk. So it can be decomposed into a classical component coefficient and a quantum operator.
I see. I was just asking if did you look at some example different in which you don't have like the typical jumps on energy levels to see how it works in practice, your approach. I mean, you
You
said,
mean,
for example, that you have a stationary state, which is the equilibrium state and so on. But I mean, in other cases, if you look at that yet.
yeah, actually, I didn't prepare any slides showing any examples, but yeah, actually, yeah, you can apply the formalism to any cases. So actually, I think you can calculate for any cases.
Yeah, thank you.
Sorry.
So there is a hand raised, Pranay Nayak.
Hello.
No.
Hi, go ahead. Thanks for the nice talk. I have a simple, silly question. Maybe could you give me some intuition on your one-way flux and the current operator?
Thank you for your question. Yeah, actually, at this stage, it's not so much clear why these choices are intuitive. So, in fact, yeah, for the validity of this choice can be verified through some more practical results, I think. So, for example, you can derive some like uncertainty relations or some inequalities, and by combining the gradient and current, we can recover some time derivative like term of the observable. So that's like the current in the classical case. Actually, from this form, I don't think we can learn some intuitive things.
I see. Thank you.
Thank you.
Okay, there is another question by Olga Movilla.
Yes, hello. So I was wondering it was a lovely talk, by the way. I was wondering, seeing the structure is very reminiscent of some sort of non-commutative optimal transport scenarios that I've seen elsewhere. So I was wondering if you had explored that and whether you can build some optimal transport on this.
Yeah, thank you very much for your nice question. Yeah, that's a very important question. And yeah, actually, the results, to be fair, my result had referred much to the optimal transport community, non-commutative optimal transport community. And but by now, I think connecting the result to optimal transport is still challenging, because this structure only discusses the dissipative part of the dynamics, while the whole dynamics have the unitary term as well. And so this unitary term doesn't exist in the classical case, which enables us to connect directly the thermodynamics and optimal transport. But currently, I think it's very challenging to find connection between this kind of formalism and some genuine optimal transport.
Okay, thank you.
Thank you.
Okay, so let's thank Koei again, and let's move to the next lightning talk, which is going to be given by Loris Maria Cangemi. So please, Loris, may you share your screen? Yeah, so Loris, if I understood well, is postdoctoral researcher from University of Naples Federico II in Italy, and he's going to talk about probing quantum anomalous heat flow using mid-circuit measurements. So thanks for participating, Loris, and the stage is yours. You're mute.
Thank you for having me here. And I would like to talk about probing anomalous quantum heat flow using mid-circuit measurements. Actually, this is a project I was involved to while a postdoc at Bar Ilan University in Israel, working under the supervision of Amikam Levi. And here is a list of my collaborators, different people who took part in this project. And here is a preprint for more details about this. So here is a brief outline of the talk. I will briefly recap on the importance of anomalous quantum heat flow and its relevance to quasi-probability distribution. Then I will move on to our experiment, and I will present briefly our results. So it's very well known that stochastic thermodynamics correctly describe heat and work fluctuations. But however, when we have a quantum system, a composite quantum systems where two parts, two subsystems share quantum correlation at initial time, we know that exchange fluctuation theorem cannot work anymore. So to solve the issue, the two-point measurement scheme was employed that accounts for the statistics of energy differences at the start and at the end of the protocol by introducing measurement at initial, measurement gates, let's say, at initial and the final time. However, if we do a projective measurement at initial time, we totally destroy the quantum correlation present in our system. So alternative schemes have to be adopted. And in recent times, the quasi-probability distributions route has experienced the renewed interest. And on the other end, many experiments on measuring genuine quantum heat backflows in quantum coherent platform have started to appear. So this is to set the stage of our work. We wanted to perform an experiment on a quantum coherent platform that can probe this anomalous quantum heat flow. So here we consider a composite quantum system described by this state here, rho CH, that is locally thermal. This is that we can label the subsystem by C and H, meaning the cold subsystem and the hot subsystem, and locally they are described by thermal marginals with different inverse temperatures. However, they are allowed to exchange energy through this Hamiltonian that is described by this parameter here, theta, and unitary ruling this interaction, we assume it to be energy preserving. That means that the energy that is exchanged is exchanged by C towards H is the opposite, just the opposite of the other way around. And we can define the quantum heat as the difference between these averages. Now we know that this quantum heat is can be written in terms of Kirchhoff-Dirac quasi-probability distribution as follows. And here we know that these probabilities actually can turn negative. Now, what is the difference? In order to understand the importance of this quantum heat, we need to investigate what is the difference with the heat we could measure, for example, by a TPM scheme. And here I recap this difference. Basically, for the quantum heat, we need two different circuit schemes. The first one is, in the first one, we do this measurement of our correlated system. And in the second one, we first let the system evolve through the unitary U. And then after the unitary, we project and measure and do our statistical measurements. On the other hand, in a TPM scheme, we perform two measurements at the start and at the end. And clearly, the heat that we can measure is different, as we label it by SG, meaning semi-classical, because we washed out all the initial correlations. So how these quantities are related? Then it has been proved that these quantities are related via this inequality that holds whenever the quasi-probability distribution is positive. That means that if we probe violation of this inequality, then we are probing signals of negativities in the quasi-probabilities and genuine quantum effects. So we could have also direct flow of heat, both direct and backward heat, but their magnitude need to exceed this balance. So let's present briefly our experiment. Our experiment was done on an IBM quantum machine, and besides the physical qubits, we used a couple of ancillary qubits in order to prepare the initial correlated states. And the initial correlated state is prepared with this by means of this circuit, and the endpoint result is that we can theoretically prepare this state that has thermal marginals controlled by this parameter Tc and Th. So by tuning this parameter, actually we can set suitable values of the inverse temperatures of the marginals. And then by using a unitary like this unitary preserves the total energy, provided that the gaps of the two qubits are the same, and we can easily derive the theoretical expression for the quantum heat and the semi-classical heat. And we can see here that there are clear, for a given choice of the parameter, there are clear patterns of deviation, of violation of the inequality. So these patterns are what we are gonna to prove with our experiment. So translating to the IBM quantum machine, we need to run these circuits, the two circuit scheme, and separately the TPM scheme circuits. And here are our results. The first results I'm gonna present are taken from IBM Quito processor. And you can see that the quantum, for what concerns the quantum heat, there is a good agreement with theoretical results. However, if we look at the semi-classical heat as as measured with the TPM scheme, and so by means of mid-circuit measurements, we find very bad results, very noisy results that prevent any probe of any measurement of possible violation. However, if we shift to other quantum processing unit, like for example IBM Manila, the story is totally different, because we see that a very good agreement of the quantum and the classical and the semi-classical heat flow, and this allows us to directly probe the violation of the inequality, the pattern of violation of the inequalities, while residual deviation can be explained by means of simple decoherence argument. And the difference between the other quantum processor is that this processor was suitably optimized against mid-circuit measurements. Another comparison we can do is to probe the total energy conservation of the two experiments, and we see that while in the quantum case the total energy is correctly zero as expected, in the semi-classical case with mid-circuit measurement we experience this deviation. But this deviation can be accounted for by means of introducing a spam error that means state preparation and measurement, so that we are basically measuring a state that deviates from the desired one in a way that we can actually explain. So once we correct this, once we introduce this simple correction in our prediction, we agree, we achieve a very good agreement with experimental, with theoretical results. So to conclude, we provided experimental evidence for anomalous quantum heat flow that is a signature of negativity of the quasi-probability distribution, and so pointing towards genuine quantum effects on the IBM quantum machine. And also we checked our experiment against the stability, we checked our experiment regarding the stability against mid-circuit measurement, finding that the detrimental effects can be accounted for in a meaningful way. So thank you for your attention.